Kia ora koutou. Hi everyone, I'm Tony Holden and welcome to the latest installment in the NZSEE webinars GNS Science Project Lead for the 2022 National Seismic Hazard Model Update. He will be providing us a sneak peek under the hood of this world-leading science endeavour. Now, in way of brief introduction, Matt obtained his PhD in seismology from ETH Zurich in 2003, followed by a postdoc at the US Geological Survey. Matt's been actively involved in many earthquake responses over the last 20 years. This includes working with GNS's earthquake hazard and risk forecasting teams to provide forecasting data and probabilistic modelling to assist in event response and subsequent recovery phases. Matt is a member of the New Zealand Society of Earthquake Engineering and an associate editor of the Bulletin of the Seismological Society of America. Now, for those of you who haven't attended previous webinars in the series, the chat tab is locked, but we encourage you to ask questions through the Q&A tab, and we'll try to get to as many of these as time permits. Okay, Matt, I'll leave it to you.
Thanks very much, Tony. Let me get my screen up here. I've got too many windows open. I think I'll just do it this way. Hopefully this will work. Okay, so hopefully everybody's seeing my full screen now. So before I get started, I'm presenting work on behalf of a huge number of people who have contributed to this. And with me here today, I've got Anna Kaiser, a seismologist at GNS Science, and she's led the work that's been happening in the basin space. And I've also got Sanjay Bora, who is also a seismologist at GNS Science, and he's been working quite intimately with all the ground motion models and ground motion data. So they're both here to help with any particular questions or thoughts people have on that space. So I'll go ahead and get started now. So just, I guess, on this theme that it is a very large team that's been involved in that's been kind of designed from the outset. It's a very large global collaboration, and there are, I guess, two main reasons that we've done that. One is to really bring in the best knowledge from across the country and around the world, just to make sure we've got the best science going that we've got in the model. But also, when we've got something as complicated and as complex as earthquake forecasting, there's no such thing as consensus on this, and it's not even reasonable to try to aim for that. So we've started from the beginning to try to represent the broad range of opinion and the broad range of our understanding about earthquake processes, and that's really been our goal. So to that end, we've got more than 50 scientists from around New Zealand who have been involved around the world and New Zealand who've been involved in the project. So that's from across universities and CRIs and across many different countries, from different types of organizations. And some of the key collaborating institutions internationally have been the USGS, who we've been quite intimately involved in various parts of the model development, Global Earthquake Model, Geoscience Australia, and GFZ Potsdam, but many others have been contributing. When you're, as everybody knows, when you're doing any sort of science or any sort of project like this, the review is a critical part of that project, and it's particularly challenging for something as big as this with a team as big as this, and something that was done on such short time frames like we needed to do for this. And in the end, we had more than 30 reports that have come out. And to get solid reviews of those, we've used what we call a participatory peer review process. So that means we effectively had the review team embedded in the project since the beginning. So we had about 17 people involved. About half of those were international scientists, so other national model leaders from around the world or other key topic individuals who could provide input. And then the other half were more what we would call technical end users, so people needing the outputs of the model from different industries, as you'll see there. And I guess the goal of that was really twofold. One was just to make sure that what we're providing was usable and that we're targeting it right, and formats and things like that were the right kind of thing. But also a bit of back and forth between the two communities, and something I think we need to work on a bit more is understanding we need to understand, keep always making sure that we understand how the model is used and what people might need, but also trying to make sure that people understand the model itself, because there's different assumptions and different things used in the model, and to best use it, get the best use out of it, it's good to make sure those are understood. So that team was involved at quite a detailed level. And then the last part was this so-called assurance review, and this was another international review process that was kind of placed across the top of things, and that's the team that looked into the science decision-making process, the peer review, and so on, and that was all positive outcomes. And there's a report online if anybody wants to see what the outcomes of that was. So just at the very basic, I'll go through just the basics of how we put the model together, and then look into some of the kind of the factors that matter the most, and then look into some of the results. So just at the basic level, I think everybody understands this. We're producing estimates or forecasts of shaking for the next 100 years. A very typical output of this is a mean map of the forecast. And the basic idea is that the future will look a little bit like the past, but a little bit part is where a lot of the judgment needs to come in, and where our understanding of the different possibilities and our different understanding need to come in. And what that means is that in the end, we don't just have a single forecast. There's not just a single number, but we have a distribution on what that forecast is. And that really represents what we understand about future earthquake shaking. But it's a fundamental change from the type of information that we put out in the past. And of course, we want to know how good the forecasts are in the end. And there's a number of factors that I won't go into details about here, but really this heavy review process was a big part of that, really to ensure that we've got the best available science. And then there's a few other factors. So we're fitting to the data into most of the model development process and how we do that now. And we also do some post hoc tests to look at how it fits consistency of the observed shaking that we've had in the last decades. And really all of this is just to ensure that we've got our best knowledge in there, and the best available science is being used to constrain the model. So just to be clear on this one, the national model stops at the shaking. We're only doing the hazard. We don't get into impact. There's no risk. We're really just focused on what's underground, and then we hand that off to many different end users who are really using that for risk-based decisions. And just a point I wanted to make here is that to make risk-based decisions, and even just to use the national model its own, it requires that a community understands their own risk tolerance, because depending on what output of the model you used, you're implying there's a different risk tolerance, and people need to think about that when they're using the model, and then they're looking at different probabilities. Okay, so now I'll get into a little bit of how we put it all together, just I think building on from what Brendan talked about last week. I guess the brief summary is it's a model, but it's actually a collection of many different component models. So the first part is just the earthquake ruptures. So this is what frequency and what magnitudes. So here we're looking at the fault model that we've used. So the black lines, those are the crustal faults. So the Wellington fault, the Alpine fault, the Aotearoa fault, and other faults that kind of we all know about. And then this shaded region here, that is the Hickory-Kermadec subduction interface. And if you've looked at these types of figures before, you may notice that in the past it was terminated about here. It actually extends on quite a bit farther. We've stopped about halfway to Tonga in terms of kind of where there is a semi-natural barrier, but also gives us quite very large low probability ruptures. And then down at the southern end here is the Pusiger subduction zone. So in all, we have about 1,000 faults in the fault model. And from that, we build hundreds of thousands of potential ruptures. And we do that either by breaking down these faults into smaller sections that might go kind of on their own, or looking at how the ruptures, the different faults can all connect up together. But even though we've got 1,000 faults, we know we don't have them all. And so we do that by modeling another hundreds of thousands of random ruptures, and that's constrained in different ways that I'll talk about in a minute. And then the second part is the ground shaking part. So that's given all those hundreds of thousands of ruptures, what is the range of possible shaking that we can have across the country when we consider all of those? So we do this using many different models. So a change from the past. Some of these are internationally developed models, and some of these are models that are specifically optimized to New Zealand. And we need to use a range of models because there is significant uncertainty in what may occur. And then using this range of models allows us to include that in the model. And importantly, each one of these models can give a different forecast of the shaking for the same rupture. So then we take all these hundreds of thousands of ruptures, then we look at all the different models of shaking that can happen, and we integrate across all of that, and that's what gives us the hazard estimates in the end. Okay, so just wanted to talk a little bit about what we do to put it all together, what we need to think about when we put it all together, and how kind of the past relates to what we're doing. So all components of the seismic hazard model are either constrained by past observed New Zealand or global earthquakes, that's instrumental, historic, or prehistoric, or our physical understanding of earthquake processes, or most often it's some combination of both. And we have different data sets to do all of this, and each one of these gives us a different snapshot into the past with different implications for the future. Each one of these data sets has different strengths or different limitations. So for example, we have earthquake geology, which goes back tens of thousands to hundreds of thousands of years, where it's only limited places in space that we've got that information. Then we have kind of earthquake location and magnitude, say the GeoNet earthquake catalog, that goes back 1 to 200 years with obviously increasing quality as we get closer to the present. Then we go back to the more recent decades, we get the earthquake shaking amplitudes that's used to constrain how much shaking we may have. And then even kind of the most shortest time frame that we have in terms of the major data sets that we use is the geodetic strain rate, which goes back a couple of decades. So while all this matters is that earthquake processes occur on hundreds to thousands of years timescales. So previous earthquakes, say the Darfield earthquake, a Darfield-like earthquake occurred more than 20,000 years ago, and a previous Tohoku, Japan-like earthquake, so the 2011 magnitude 9, occurred more than 1,000 years ago. So if we're looking just say the past 100 to 200 years in New Zealand, we have not observed earthquake magnitudes that represent what we know can occur from the geologic record or from what we've seen in similar tectonic regions around the world. And if we look at the last 20 to 30 years, then we certainly have not observed a shaking from earthquakes that we know represent what we can have based on the geologic record or from similar tectonic regions around the world. So what we do then is we start out kind of at our base layer. That's where we have the New Zealand data, and we use as much New Zealand data as we can. We take it all, and this provides us with some sort of starting constraint on what might occur. And then we go from that then to look at global data, and we supplement with as much relevant global data as we can. But even in that case, we're deficient in some key, say, region or types of data that we need. So then that gets supplemented with either kind of statistical or physical models of our understanding of earthquake occurrence. And I guess the upshot of all of this is using just NZ, or our understanding of earthquakes from the last 100, 200 years is a poor indicator of future shaking. So we really need to go to bring in all this other information to understand what may occur. So Brendan talked about the PSHA framework last week, and that really provides us the framework to putting in all of these different data sets, but it doesn't constrain what it is that we actually put into it. So that's a framework that we combine all of this other information together. So here are some of the key conceptual differences from previous NSHMs. I've already talked about uncertainty. That's obviously a big one, is a critical part of what we're doing. It allows us to get our real understanding of earthquake occurrence into there. It means, though, that we don't have a single answer in the end. We've got this distribution. The results include influence of multiple data sets and scientific hypotheses that just really, again, same thing, lets us get our understanding in there better. In the end, we end up with thousands of potential ruptures rather than a few hundred than we had in the past. This allows for a range of things, including better constraints on the hazard estimates, but it allows us to get complex and multi-fault ruptures, which is something that was very difficult to do in the past. And that allows variability in magnitude and rupture length, which I'll talk about in a second. And maybe less in the hazard context, but importantly in a risk context, is this allows us to get in high impact, low probability earthquakes, which is something that's been difficult in the past. Quite often when seismic hazard models get put together, they're very, for obvious reasons, they're very focused on higher seismicity regions, but that leaves a bit exposed to lower seismicity regions, which are a bit harder to do in some ways because we have less data there. But we've worked on some very specific models for our lower seismicity regions that account for the greater uncertainty that comes from that lesser amount of data that we have. and that this has been important for those regions. We've moved to a 100-year forecast from what in the past has been considered a time-independent forecast, and we've argued that for various reasons that really get at that allows us to much better constrain kind of how we look at the uncertainty and what we may put into that. But we can't. It's still an annual rate in the end, and we can look at shorter-term forecasts. So probably if we had to just take one thing that's had the biggest impact on everything, that's the ground motion modeling side, and that comes in two ways. One is the use of many ground motion models rather than just a single one. So that's this internationally and the New Zealand tuned models. But importantly, we've got additional data now, and that's changed how we understand the additional data and knowledge, and I guess that's changed how we understand what shaking may occur. And then the final one is just simply how many earthquakes will occur over the next 100 years and what models we use to get at that and how we understand the variability in that. So looking at the seismicity rate model side, so the source side, we've got kind of 4 high-level components. The first one, we call it the inversion fault model component. So that's what we're putting onto the faults. And if you're familiar with USURF3 or what they've done in California or what they're looking at in the future, we followed a very similar method, and we've worked very closely on them. And that's what allows us to get these multi-fault complex ruptures and the uncertainty around magnitude lengths and so on. The next one is the distributed seismicity component. This is really just a spatial component, not the rates itself. And we have 2 different models here, one targeted at the higher seismicity areas. And this brings in much more information than just an earthquake catalog that has been typically used. And then we have this uniform rate model, which I'll talk about in a minute, that looks at the lower seismicity areas. And on top of that, then we place the overall rate model. And that's where we're looking at different ways to better model. So earthquakes have tended to be assumed independent of one another in the past, and we know that's not right. But it's been tricky to get it in there, and we've managed to include that in this model, and that allows us to get much better kind of number forecast than we could do in the past. And then the fourth part that tends to get overlooked a little bit, but is actually pretty important to the model, is the slab model, and that's just the logic tree that's used for the downgoing slab earthquakes. So what are the changes to the model that matter most for in the hazard sense? And I'll go into each one of these in more detail. The first one is the rupture complexity. The second one is the Hikurangi-Kermadec interface, how we model those sources. The third one is what we're doing in the lower seismicity regions. And then the last one is just, as I've just said, is how many earthquakes do we expect to occur. So I've talked about in the past, so you may be familiar with this concept, but just an easy way to talk about it, the rupture complexity is just to think about it in terms of Wellington. So we no longer have just one Wellington fault rupture with one magnitude and one rupture length. So we know ruptures can be complex and not just a straight linear movement on one fault. We've seen that in Kaikoura. We've seen that in pretty much every historical earthquake that we've mapped in the country. There's uncertainty in magnitude and length, and we have many different data sets. Each one of these gives us a different ability to constrain these fault ruptures, and we need to include all of those in our understanding, and that's what we're doing now. So just as an example of what that would look like for the Wellington fault, if we look at the magnitude frequency distribution first on the right, we've got the magnitudes that we're considering. Here is the annual rate. So this is the distributed seismicity component. So ignore this for now. We have many different models, and this is just one particular model. But this is just looking at the range of magnitudes that we're seeing on this one section right here of the Wellington fault. So in the past, we would have just considered a single magnitude and rate. So I've just plonked this dotted line on here, so it's not exactly in the right place or with the right rate. But that's what would have been considered in the past. And now we're seeing this distribution from magnitude 6.8 to something greater than 8. And what that comes from, if you come back to this particular figure, is its connectivity with other faults in the region. So any other fault in here that is colored is a fault that at some time joins, and they need to be connected, but it joins in a rupture with this section on the Wellington fault. Note that this is a log scale, so that most often this segment is going on its own. but at not insignificant rates, it is connecting up with other ruptures in the region to create larger earthquakes, and to account for the uncertainty in both the magnitude and what the rupture length can be. And we can take that same model and dive into more detail and look elsewhere. So now we'll look at the Alpine fault. So here we'll look at the magnitude frequency distribution on that. Please just ignore the lighter green. That I just couldn't get rid of that. The dark green is actually what the magnitudes are looking like in this particular model for the Alpine fault. So we're looking at magnitude 6.8 to magnitude 8.6, with the bulk of them being greater than magnitude 8, as we would expect. And here is the section that we're looking at there. And here is the connectivity in the fault network of ruptures that may connect up with this particular segment. Again, notice that it's a log scale here. So most often it's going on its own, but we know it can connect up with others, and that's what we're doing. And just to show kind of some of the other kind of constraints that we're looking at, this is looking at that particular section along strike. We know what earthquakes have occurred in the past and kind of what rate they've occurred at. And this is just showing how that's fit actively in the model. And at the same time, we also fit the slip rates along the fault. And you can see it's getting the slip rates quite well. And it also fits other information at the same time, but these are two obviously important ones. Now in the Hikurangi is another critical one. I won't say too much here, but basically we have additional data, and our ability to model a more realistic range of ruptures and magnitudes has changed. So this is one particular model of many. Again, this is the slip deficit rate model. So what that means, this shows kind of this based on the geodesy. We know that this particular patch on the Hikurangi interface hasn't moved since we've had geodetic data available. And that's showing the higher slip deficit rate in there than the surrounding part of the Hikurangi, because it hasn't been moving, whereas these other parts have been moving in slow slip events and so on. And you also notice it's extended a bit further to the south here. And this is just showing examples of, in this one model, rates of magnitude 8.8 to 9 that we see, with the higher rates reflected down here due to this locked patch, and the overall rates of magnitude 9+. Again, note the log scale. Most of the bigger events occur up here where the rates of events are quite high, but sometimes they come through down to the Hikurangi. Okay, lower seismicity zones. This is the uniform rate model. So these are the one ways that we specifically targeted the lower seismicity regions. And as I mentioned, these regions are poorly characterized by locations and rates of historical instrumental earthquakes. So to account for that, we're using a much reduced spatial precision, because we just can't be precise about saying where the future earthquakes are more or less likely to occur. So we have these broad regions where the rates are all very similar. And the more important than that, and it gets quite heavy into the statistics, so I won't go into it today, but we have now an occurrence rate model that accounts for the bias that we have when only a small number of earthquakes are observed. And these two things together are then kind of resulting in increased earthquake rates in these lower seismicity regions. But this is really the key one. And this is something that we see very strongly in New Zealand data and in Japanese data. But interestingly, when you look at, say, California or Italian data, it's not there. And this really comes down to different characteristics of how earthquakes cluster in both places, and cluster on kind of longer timeframes. Then the next one is, as I mentioned, how many earthquakes will we have? The first part of that was a significantly revised and updated earthquake catalog. If you've heard me talk in the past, I've talked a lot about magnitude estimates, and they were all over the place through time, and that actually has a pretty significant impact on how many earthquakes you might estimate for the future. So there's a lot of work to kind of homogenize that magnitude going through time. So you may not know, you can't just download the GeoNet catalog and use it for these types of calculations. You'll introduce all types of problems. So there's a lot of work done on that. And interestingly, just if that's all we did, that would actually bring the hazard down. But then we also needed to look at better ways that we can constrain the statistics about how many earthquakes we've actually had in the past, which is actually quite challenging to understand how many we've had, but then how that translates into future events. And that looks at models that can better capture the variability in the rate, knowing that earthquakes really aren't independent of one another in time. And we also bring in global constraints to make sure what we're getting out of this is quite reasonable on the global scale. Okay, take a drink here. And I'll shift to the ground motion characterization model, the ground motion component. And really there's two big changes here that I mentioned earlier. The first one part of those two big changes is the move from a single ground motion model that we've had in the past to the use of multiple models. So these are the logic trees that we're using. So on the left here, that is our crustal logic tree. For this, we're using the NGA West models, for those familiar with that. So those are models constrained on global data. And then we've supplemented that with Peter Stafford. Many people here probably know him, who did a New Zealand backbone model based on the new ground motion data set that's come out of this. And Gail Atkinson has also developed a New Zealand backbone model based on the same data set. And we represent all of those within the model. And both the Stafford and the Atkinson models came with their own epistemic uncertainty, so their own ranges on that. So that's what's represented in these upper and lower bounds, or that range on that uncertainty. And then we've done the same for the other global models, which get treated kind of at the same level as the Atkinson and Stafford models. And for the interface and for the interslab logic trees, we're using the NGA subduction model. So those are very new models, and I'll show a bit more about that in a second, as well as the Atkinson New Zealand backbone, which also had an interface interslab component. So you couple the range of models that we're using now with just significant changes to how the ground motion modeling is done based on new data that we've had. So we've got very large differences from the 2002 and 2010 model to the current ones. And this is just an example of a difference from the interface. So we've got on the order of 25 years of additional data and advancements in our understanding and our ability to model the ground motion shaking. And that's resulted in different spectral shapes, different magnitude and different scaling. And we see similar orders of differences across the crustal, the interface, and the slab models. So this is just looking at a direct comparison, which I think illustrates reasonably well where that sits. So the colored lines, these lines here are for the interface. Those are the new models with the dashed line representing the epistemic uncertainty bounds, so the upper and lower bounds on the Atkinson model. And then the light blue line here, I think it is, represents what was used in the 2002 and the 2010 model. And you'll see very different spectral shapes that you see in this particular plot with very, very high frequency shaking, very different predictions. And then a different slope with kind of the medium spectral period range. You see much higher predictions coming out from the previous model than compared to the current models. And all of these factors together really influence the hazard that we're seeing. And I'll show a few other plots about that later on that might help explain that more. So not everything we've done is bringing the hazard up. So one adjustment that was done in the 2002 and 2010 model, but actually isn't present in the NGA subduction model, is an adjustment for the back arc attenuation. And by that, I mean this particular region of the country where we know the crust here and the mantle actually has pretty significant attenuation impact on the data, but that's explicitly excluded from these NGA subduction models. So in the 22 national model, we put in this adjustment factor based on the BC hydro model. And what you'll see here, we've got PGA and 0.5 second spectral acceleration plots. Here are the predictions coming out of a particular model when it doesn't account for this adjustment factor. And the red dots here are the observations that we have within this back arc region. So you can see there's a pretty significant reduction in the amplitudes within that region. And we've applied this BC hydro adjustment factor to account for that. So that's actually had a significant impact on bringing the hazard down in particular locations. And then the last one in this space is also a reduction in general, and not all of the NGA subduction models or the Atkinson 2022 model account for reduction in uncertainty due to soil nonlinearity. So this is just showing some some features of, or the impacts of that. So on the y-axis, we're looking at the uncertainty. Here is the spectral period, and the dashed lines show the corrected model for this nonlinear soil response. And you can see a fairly significant impact across most of the range in terms of this bringing down the uncertainty on the ground motion calculations, which then brings down the hazard calculations in general. And the last one in the ground motion space that I'll mention is related to the basin effects. So what was done in the past models was use of the single McVary model for the ground motion calculations, which didn't explicitly include any basin effects. And we've used this range of ground motion models now where they don't explicitly include basin effects as well, but they do include some broad average global basin behavior through the Z1 term and so on that we've used in a very generic sense. So that was all we were able to do at this point. I mean, timelines on this project were very tight, and there's been a lot of work done within this project to develop the 3D geological model and to make progress towards next steps, which we expect to be having more results coming out over the next 8 or 10 months or so in terms of much better regionalization of what this might all mean in terms of ground shaking, in terms of basin effects. Okay, so now I'll get into the hazard results. So everybody may be familiar with this, but just in case, I'll start with some of the basics. We tend to show everything in probability of exceedance. I know in general, people prefer return periods, but return period is actually not strictly correct, and it can be misleading in some ways. So we're really trying to encourage people to get their heads around probability of exceedance and to use that a bit more. So what this actually means is how likely are we to experience this amount of shaking or more in a particular time period. So for example, we have a 10% probability of exceedance in 50 years or 2% probability of exceedance in 50 years. Obviously, this is the 10% probability of exceedance in 50 years is a main one that's been used in the standard. A lower probability means necessarily that it's less likely, but it necessarily means higher shaking levels. And this is where these ideas about risk tolerance come in, and where are these particular thresholds that are getting chosen coming from, and how are those relevant to, say, other decisions that are being made. VS30 in sight, I think probably everybody's well aware now that we moved to VS30 because that's what we have through these international models. And I guess all I'll say here is this adds a fair bit of, as people have seen, this adds a fair bit of fuzziness in comparisons to the current model to past models. And that's because we don't have a direct mapping between VS30 and New Zealand site class. So not comparing apples to apples. And I'll show, probably everybody's seen it now, but I'll show some examples of what I mean by that and the impact of that. And then, of course, there's the various ground shaking metrics, amplitude metrics. And the reason I'm pointing all of these out is that depending on which parameter you choose in any of these, the changes to the hazard can vary quite significantly. So there's not a nice number of just one number saying this is how much the change has been. And this is why we've been focused on a range in most of the information that we've been putting out. When you kind of look across all of the data and you take into account this fuzziness that I've just talked about in terms of VS30 and so on, the hazard increases across the country range from approximately no change to more than doubling. And the average is an increase of about 50%. And of course, this, as I said early on, this is just talking about shaking. It doesn't necessarily translate to an equivalent impact for buildings or other structures, as everybody knows, and the audience knows much better than me. There's a lot of other factors that need to be considered when looking at that. So we look at just a PGA, which is a common one that people look at, just 10% probability of exceedance in 50 years on the same color scale here, so up to 1G, and you can see kind of, I get this is not a surprise. I guess we knew mostly that things were heading in this direction. We didn't know the exact details, but we see quite large changes across the country. And then maybe I'll draw your attention to this histogram over here, which is based on work that Anna's done. And this is looking at just within the central Wellington area. This is looking at a 1 second spectral acceleration. When you take into account the the uncertainty in the mapping between VS30 and New Zealand site class, you start to look at changes that look like this. So in this case, 1 means there's no change in the hazard compared to 2010. So that's looking specifically at 2010. And 2 means there's a doubling. So you can see we've got quite a broad distribution in that, with most of the sites, so this is just looking at sites across Wellington, falling at about this 50% increase number. So that's where that number has been coming from. But you can see in some locations it does get larger than that. So we don't have the same VS30 data across the country, so we can't do this in detail everywhere. But on average, in terms of when we don't account for VS30, we're seeing this is kind of a representative site for the country. So this is looking at 10% probability of exceedance in 50 years. And then if we look at 2% probability of exceedance in 50 years, the maps look fairly similar, but you can see we're looking at doubling of the shaking. So again, this is just a reminder on the whole risk tolerance thing and thinking about what particular risk tolerance is and how those numbers should be thought about in terms of a probability of experiencing this amount of shaking in the next 50 years. Okay, one last on the maps, I think, and this is just to look at the ratio of change between the 2022 model and the 2010 model. So on the left, we've got 10% probability of exceedance in 50 years, and on the right, we have a 2% probability of exceedance in 50 years. And just to simplify things, red means 2022 is greater, and blue means 2010 is greater. And you can see we've just really got this location here, Central Otago-ish, where we're seeing kind of in these particular metrics where we see something potentially greater from the previous model. But overall, we're seeing increases across the country in the new model. And you can see we've got some of the largest changes coming along the east coast of the North Island. And that's really reflecting the changes from what we've learned about both the Hikurangi occurrence model and shaking from interface events. And you may notice kind of this brighter red up kind of in Northland. And keeping in mind that that's a big change, but it's on a very small number. So we still have very small hazard up there relative to the rest of the country, but because of the changes in how we do the source modeling, largely, not entirely, we see some increases in hazard there as well. So then we put these schematical figures to look at the range of hazard changes that we see across the country. And you read these the same way. 1 means no change, 2.5 means 2.5 times the change that you'd see, sorry, 2.5 times the 2010 model. And these distributions are schematical, but they're representative. And so similar to what we saw in Wellington, the chance of seeing something at the edge of these distributions is very rare compared to what you see in something that's actually biased kind of low compared to the center of the distribution. And that's kind of representative of what we see across the country, where the edges change some, and in some cases we go below 1. But in general, there are distributions that look like this, where you're most likely to be seeing something that's somewhere between kind of 50% and a doubling of the hazard. Okay, and I get a bit more into risk tolerance issues, and I want to do that by talking about hazard curves for a second here. And then maybe something that everybody's not as familiar with looking at. So here we're looking at a hazard curve for the Wellington region. On this axis, we've got PGA again, and here we've got annual probability of exceedance. So what that means is up in this corner, we've got small shaking, but it's more likely. And down in this corner, we've got large shaking, but it's much less likely. And then we've got a distribution on the center line here. We've got a distribution of that. So these are all related to forecasts for the next 50 years, effectively. But depending on what probability level that you want to look at, you get this full range of shaking. So this star here, that represents the 10% probability of exceedance in 50 years. And this star here represents the 2% probability of exceedance in 50 years. So if I went back to those Wellington maps that we were looking at for PGA, and you looked at the 10% map, you'd see this value, and the 2% map, you would see this value. And then the other information that you've probably already figured out on this map is we are showing, the other maps I've shown you haven't shown this full distribution of information that I've talked about. We're showing it here. So this is showing our 80% confidence bounds on that particular hazard estimate. So we had 80% chance that it falls within this range for the 10% POE in 50 years. And the next bit of information is this is showing the hazard estimate that came from the 2010 National Seismic Hazard Model. And keep in mind, in that case, it was just the single estimate that we had, and that falls outside of the 80% confidence bounds of the current model. So then we can look at hazard curves across the country. So here we have Auckland, Christchurch, Dunedin, and Wellington. And just a reminder, so if you plunk this point, this point, this point, this point, you do that for everywhere across the country, you get the 10% and 50-year map. And what you can see is in general, we have slightly different hazard curve shapes for these particular ones I've shown you. It's probably not too obvious on here. Some are a bit flatter, some are a bit curved, and so that has implications for what's driving the risk, depending on how flat a hazard curve may be. But you can see fairly similar behavior with the 2010 model kind of falling outside of the 80% confidence bounds and kind of the hazard ranges that we normally would be looking in. So we can break that down a little bit more now and look at what's coming from the source model components and what's coming from the ground model components. So hopefully you can see that. I've got something covering up the screen on mine. But here we see that's the pure 2022 result. The red dashed line, that's the pure 2010 result. So similar to what we were looking at before. And this particular curve here, I'm not sure if that's gray or green, that is taking the 2022 source model and using the 2010 ground motion model on it. And the orange is taking the 2010 source model and using the current ground motion model from that. And these can be a bit tricky to wrap your head around, but I think the short upshot of most of this is that we see this orange curve is closest to the blue curve. So that's showing that the biggest influence for the Wellington region is really coming from changes to the ground motion model, but it's not completely devoid of any impact from the source model, particularly when you get to lower probability levels. And you see that even more when you go to 0.5 seconds. That the ground motion model, or sorry, the source model is making a pretty big impact at these kind of moderately higher probability levels, and as you go out to longer periods, it's almost entirely coming from changes to the ground motion model. So that's representative of Wellington and probably most of the higher seismicity parts of the country. But when we look at Auckland, we might see something a little bit different. So a reminder of the colors again. Here's the pure 2022 seismic hazard model. Here's the pure 2010 seismic hazard model. The orange is the 2010 source model plus the 2022 ground motion model. And this one is the 2022 source model plus the 2010 ground motion model. And you can see the order of these is flipped from what we saw in Wellington. So what that's indicating is that in this case, there's some change coming from the ground motion model. It definitely matters. But what's controlling the hazard changes the most is coming from the source model. And you see that across most of the spectral periods here. So that's coming from the better treatment in these specifically targeted models for the lower seismicity regions. So now we can break that down a little bit more, and we've been looking at kind of summary across all of the possible earthquakes that are all the credible earthquakes that can happen. And we can look in more detail. And I'll show these particular ones for Wellington, which I showed a preliminary version of these last year. I think they caused a little bit of confusion, and they still may. So hopefully we can get to that all right. So here we're looking at disaggregations, which show what earthquake sources matter most for the hazard in a particular region. So here we're looking at a VS30 of 250 meters per second, PGA of 10% POE in 50 years, and we've broken them down by tectonic region type. So this is looking at sources in the crust, sources in the interface, and sources in the slab. And you see in Wellington, for these particular metrics, it's largely dominated by the interface with somewhere greater than 50% contribution from that, and about 20% coming from the other sources. And this just breaks that down into more detail, and I think I don't have time to go into that. So I'll then look at 1.5 seconds, and this is where things are a little bit counterintuitive for people. So we still see it's the largest single contributor is coming from the interface sources, so a collection of sources. But you can see in this case, we've actually got to add a longer period. We've got a larger contribution coming from from the crustal sources than we had for peak ground acceleration. So I'll just show a couple of scenarios that will hopefully help understand where that's coming from. So this is looking at scenario spectra for Wellington. So in Wellington, we've got a whole range of crustal sources that say the Wellington faults that 0 kilometers to 1 or 2 kilometers away to a handful of other fairly high rate faults that are very close in distance to the central Wellington area. And then we've got the interface, which is at a distance of about 25 kilometers away from Wellington. So that's what we're showing here. We've got a 7.6 at 1K and a magnitude 8.5 at 25 kilometers. So just kind of some representative important scenarios for Wellington. And in the dashed lines, you see the spectral, the forecast and the spectral shape from a range of models coming from the interface ground motion models. And the blue, you'll see the range in spectral shapes coming from the crustal models. And you'll see that these, I should point out, there's no accounting for rate in what we're looking at. This is both assuming these earthquakes occur. This is the distribute. This is the rate. This is a shaking. So we're seeing in this case at PGA, we have the interface is a little bit lower than the crustal, but once you get out to kind of moderately longer periods, then you can see there's a significant discrepancy. And the interface shaking is quite a bit lower than what you see from the crustal sources. And this is really coming from the different scaling in the two models, including both the distance scaling, the magnitude scaling, and the different spectral shapes. Of course, when we add rate into this is going to bump up a little bit, and it brings the PGAs up quite higher, but it's not enough to make up for this difference that we're seeing in the spectral shape at these particular periods. And this is looking for VS30, and this is just showing that discrepancy goes down, but it's still there when we're looking at 400 meters per second. Now I've only got a few slides left here. Just look at things a slightly different way. So we've talked all about the hazard, but there's some uses of the model that think about just the earthquake sources themselves. And that's when you're thinking about in a risk context, things might matter a little bit differently than do in a hazard context. And we know, as we saw in the Kaikoura earthquake, more than 20 faults ruptured, and we know that earthquakes are complex. Lots of faults can go together. That's something that was quite challenging to include in the model in the past, but now using the methods that we're using, we're able to do that. It gives us more realistic hazard estimates. But in this context, it allows us to model very low probability ruptures, but potentially high impact ruptures. And here's just a particular example of that. So this is a single rupture going from Wellington through to the Bay of Plenty. Now note, this is a very low rate rupture. So that's why in this case, this particular one really won't feature in the hazard. That's a 1 in a million rupture. But this is a magnitude 8.3. We expect around 2 8.3 plus crustal earthquakes every 1,000 years. So they're not earthquakes that we can just forget about. And we know that they can happen anywhere. And this is just one example. And there's other examples depending on how the connectivity of the fault system works. But there's quite a few other different examples of how these high impact but low probability ruptures kind of fit into things. Okay, just in summary, what I've done here is just the key contributors to the increases in the hazard, and I've put these in order of relative size of impact on the hazard, with the lowest being at the bottom. So at the top, as I've mentioned, it's really for the high seismicity areas in particular, it's changes to the ground motion models themselves and the use of multiple ground motion models. Then it's how we forecast how we model and forecast the number of expected earthquakes over the next century and what the uncertainty is around that and the impact of that. And then these specific models targeting the lower seismicity regions. And right, once you get down in here, it's hard to say which one matters more, but really the complex rupture, the uncertainty and the magnitude and the rupture length and so on comes in, and also what we're doing for the Hikurangi in terms of the source model side. So just in summary, the ground shaking hazard has increased with an average of about 50% across the country. And in general, I mean, as you saw in the figures, this is just in general, the range is from no change to more than doubling. This is really just talking about the shaking. It's not about the risk, which needs to take into account a lot of different other things. And so the Hikurangi-Kermadec subduction zone is pretty clearly a significant source of hazard for the country, and it can affect much of the country, but we don't want to forget about all the other crustal faults, just thinking about the Hikurangi. The major players are still there. They still matter for the hazard, and there's many the ones I've talked about, but there's many other larger faults across the country that matter for the general hazard landscape, and maybe more important for their own region. And of course, there's small faults everywhere. We know that earthquakes can and do happen everywhere in the country, and we include the potential for those in the model. And I think I'll just take 2 minutes now, I think, and I'll just say all of the model components. So this is very different than the past, at least until the last kind of few years. All the model components, the results, and the data are available, plus 30 plus technical reports. And if you haven't had a look at it, this is kind of the technical website at this particular location. And I think I'll just show you quickly what that is. If you haven't had a look at it, please go have a look. And I've got the wrong, hopefully this is going to work. I've got the wrong thing up. But you can go in and you can look at hazard curves. So I didn't show spectra at all, but you can go in and look at any of the spectra that you want. So you can choose any. We've got 2 different ways you can look at it. You choose a particular location, or you can enter a lat long. You can look at it with uncertainty, which I encourage you to do, or you can turn the uncertainty off if you prefer not to see that. You can choose your VS30 value, your PGA value, or your probability of exceedance level. We've got hazard maps that are loaded into it. Since I'm on the wrong side, I'm not quite sure what's going to happen here. But you can, again, look at different characteristics that you want to look at, and any of this data can be downloaded. You can produce maps. We've got a whole lot of new features that will be coming, and things are getting worked on. So please talk to us if there's specific things you want to see. We're doing what we can do, and then you can go into the resources and you can see all of the science reports that are available, and you can download all of those. And I think I will stop there.
Ngā Matt, that was a great talk, and it just highlights, I guess, the mammoth undertaking you and your team have accomplished. So I'm sure we're all really, really grateful for that. We have a few questions in the Q&A tab. I'm not sure if it was mentioned. Anna Kaiser and Sanjay Boro also online, in case you've got anything that stumps Matt. But we'll start with the one on the top here. By Nick Harwood. Given the uncertainty in the modelling, how is this articulated when we are given a single design PGA value for a given location and return period? For example, in the MB NZGS Module 1 for geotechnical earthquake engineering.
Yes, I suppose that's not really a question for us, and more in terms of how that's going to be taken. And there's probably other people who are better qualified for that. And I guess the question, I assume it's likely to be a mean value, but I don't know how that would be handled.
We've got a question here from Tahura. Thanks for the great presentation and all your efforts. Has the physics-based model approach been employed at any part of the NSHM? If so, does the model give acceleration time histories at the surface? Also, was there any factor applied in the model that empowers the fault segments that do not have an active history as other segments of the same fault? If I remember correctly, there were some considerations about this in the California Cybershape project.
So maybe I'll let the physics-based simulations for ground motion haven't been explicitly taken into account of yet, but there's work happening on that. Maybe I'll let Anna comment more about what's happening there, and I'll address the second one. So there are constraints on how adjacent segments of the faults can and can't rupture together, and there's some smoothness that's required there. So that's how we bring, I think that's probably what you're getting at. So if we have fault sections, which there's a lot of that we don't have explicit data for, then they are constrained by the various sections around them and what we know about slip rates, what we know about the spatial magnitude frequency distributions, and so on. So the constraints come in slightly different ways, but maybe I'll let Anna handle the first part of that.
Right, yes, just following up on what Matt has said, although we're not using physics-based ground motion simulations in the current NSHM, we are progressing the work with University of Canterbury to look at, and knowing that this is important and can provide some constraints where we don't have a lot of data for these big magnitude ruptures we haven't seen yet. In particular, in the Wellington Basin, we're also having a look at the local amplification with the physics-based methods. So at this point, we've got some validation of small earthquakes, looking at the spatial variations and the spectral variations around the city. So that's where we are right now, and we're looking to progress that work over the next phase to come up with some more varied answers on different earthquake scenarios, as well as some understanding of the uncertainty.
We've got a question here from Kevin Foster. Are the fault segment connectivity assumptions based on seismologistic judgments, observed events, and/or are they based on some simple geology heuristic, e.g. connectivity possible with max distances of X meters apart, etc.?
On the first questions, it's a bit of both. It's informed by what we've seen in the field, kind of around the world, and all the research that's happened on that. There's judgment in any of this that we do, no matter what. But it's also heavily informed by, I guess the last question was about physics-based modeling in terms of ground motion, but we've also had a lot of input into this rupture connectivity from kind of physics-based modeling of kind of the whole fault system and how ruptures connect up together, and that comes into kind of how stress gets transferred around when faults are slipping. So that's provided some pretty heavy guidance on what's possible. In the past, what was done in USERF 3, the California model, it was really based on kind of what you say in the latter part there, into some kind of simple geometric constraints and so on. And we've done both. We've done it both ways, and we actually don't see significant differences in the hazard if we use kind of more simple geometrical rules, or if we used kind of these rupture sets that are more guided by what the physics is saying that they should be. And when I say it's guided by the physics, but no matter what, there's the same observational data that's helping to constrain what goes into those physics-based modeling. And the last one about max jump distance, that's actually something that we spent a lot of time looking into, because that's probably the biggest unknown. And I get the simple answer of what we found out is that it doesn't actually matter all that much for the hazard levels that we're interested in New Zealand. So I think there's very strong evidence that it's pretty hard to refute. Up to jumps of, say, 5 kilometers are very possible, and most of the New Zealand fault network gets connected up when you have 5 kilometers. So what we did is we then allow, if there's not something within 5 kilometers, you can go to something larger. And that actually didn't have much impact on the ruptures that we see. And it certainly didn't matter in the hazard space. Maybe when looking at some of the rupture connectivity in the kind of the risk space, some of that comes in a little bit more. But in terms of the uncertainty introduces, it's pretty minor. So we didn't bring that into the final model, although we explored that throughout everything we did. And we just found that in terms of what actually matters in terms of hazard, it was going to make no difference if we looked at a range on that max rupture distance.
Question here from Pedro. Looking at the future and next steps, when it comes to local effects, are there plans to incorporate topographic amplification?
That's that one for Anna.
Yeah, I mean, this is a really good question. I think topographic amplification is another thing that we're looking at for the future. I think the first step for us in the next phase of NSHM, now we have a really good ground motion databases and so on, is to do a bit of a sweep of some of these other site parameters to see how correlated they are with the ground motions that we observe, if there's some systematic ones that stand out as being important. And that would then inform some of the future research directions to sort of understand how we might tackle that. But that is perhaps a little bit further down the track than first looking at some of these local basins.
All right. That's our last question, and we're right out of time, so that's perfect. I'd like to thank Matt, Anna, and Sanjay again for their time today. And just as a reminder, registration for the next installment in the webinar series is now open. NZSEE, NZGS, and the Tunnelling Society are pleased to invite everyone to a presentation on the seismic design of underground structures. Dr. Andy Dodds will be presenting on seismic design for the Central Interceptor project, and Wataru Okada will be presenting on seismic design aspects of the City Rail Link tunnels. This webinar is actually a live streamed in-person seminar at Becca in Auckland, and it's next Wednesday on the 23rd. And those who are attending are invited to join from 5 p.m. for refreshments and networking ahead of the seminar that starts at 6 p.m. Again, thanks everybody for attending this seminar, and have a great afternoon. Thank you.